Yeah, so hello everyone, and welcome to our training program. This is training program 3, which is being organized by the International Astronomical Union Women in Astronomy group. And we're basically doing this because we feel that training students in skills is what can actually help them in going ahead with their careers in astronomy. And so what we've planned is for this training program. So we have the chair 2 here, Mamta, and what I've planned actually is this training program. It's covering you through a set of things. Like today we talk about exoplanets. Tomorrow we are going to do photometry. The third day we'll be doing HR diagrams, and then we have dark matter and AGN spectra. So basically what I'm trying to do is just giving you all a peek into how do you actually do data analysis in these various fields. So what we'd be showing you would be, kind of basic, but reasonably good level so that you can actually see how do people apply it onto doing it for papers. So probably after this, if you were to pick up a paper, like after today's session on exoplanets, if you'd pick up a paper on Kepler data, I hope you would, find it understandable and you'd understand how they actually get all their parameters, right? Another thing is that many of you all have inquired about the Slack connection. So you can go to our website, and there's a new link over there. I'm also posting a chat, and I will send it to you in the email too, which I'll send it to you today evening. But I'll send you the PPT which I'm you now. I will be mailing that to you, and we'll then do that. So let's start with our thing. Are there any questions or anything somebody wants to ask? Yeah, okay. I also should mention is that for this session, we'll be using Topcat. So in training program 2, I had covered Topcat. Those who did not attend it, you don't need to worry. It's a very simple thing to install, and I will help you to install it. So don't worry about that. The rest of the software, I'll add it in the mail today, which is APT tool and DS9, which you can then install it. We will need it for tomorrow's session. But today we just need Topcat. And if you don't have Topcat, you can also use Excel or anything that will help you handle spreadsheets, right? So I'll start off with my thing today. Two questions. Kepler data, and we'll actually, I would also like to acknowledge
Just stay online. The speaker will connect soon. Can you all hear me?
Yeah, we can hear.
Yes, sir.
Yeah. Yeah, just a moment. Priya will reconnect. Just a minute.
Yeah, I'm sorry for that, this thing. Unfortunately, there was a problem with the net. Okay, so, ठीक है ना? Okay. So we, like I said, I'm going to be talking about Kepler data, and this I would like to acknowledge my thanks, big thanks to Tim Hamilton, because Tim Hamilton had done a similar session for us earlier, and many of the things I've taken from this session are actually with his kind permission, which I've been using it today. So big thanks to Tim Hamilton. Okay. So Kepler is basically a telescope which was, okay, I can probably show you a little bit about Kepler, and we can, let's see, have anybody, any of you all heard about Kepler? Is there somebody who's heard about Kepler? Yes, okay. So Kepler, let me, yeah. So I hope you all can see my browser over here, right? Right. Now, Kepler was a satellite which was basically the Kepler Space Telescope was basically a satellite, a telescope which was sent out to space with the basic, this was the thing. It was a telescope, and here I'll get onto it. So what you can see is what it basically did is looking for exoplanets is a difficult job. Okay, and there were many methods of actually looking for exoplanets, of which the radial velocity technique was actually the most popular one. That if you have a planet going around the star, then you would actually get a shift in the spectra, which you can actually do by measuring the radial velocities. Now, Kepler was a mission which was sent, a telescope itself, a 1.4-meter telescope, which was sent to actually look at a set of stars in a small region of the sky. Okay, and what it basically did is it followed this method called the transit method. So the transit method is a method in which if you have a planet coming in front of the star, the light from the star will obviously get, will fall. You can see there's a dip in the brightness of the light coming from the star. And this is what is called a transit. Okay. And I'll go back to my PPT, and we'll look at that. I'll talk about Kepler a little later in more in detail later on. But essentially what Kepler does is it basically looks at stars. And if you have a planet going in front of the star, you will have a fall in the brightness, right? So if this is the brightness from a star, when the planet comes in, a certain part of the surface of the star gets hidden. So there's a fall in the brightness, and then it comes up again, right? And this is what is called a planetary transit, okay? And in a transit, what happens, there's this fall in brightness. And this fall in brightness, or this transit method, is a standard method which is used to detect exoplanets. And that was what was used in Kepler, right? So again, over here, what you can see is obviously the depth in which you would have this fall in brightness obviously depends upon the ratio of the squares of the star and the planet, right? And depending upon that, you will have a fall in the brightness, okay? And for example, this is an example of one of the exoplanets observed by Kepler, which is called HAT P7b. And you can see that this planet, we'll talk about hot Jupiters also very soon. You can see that if we normalize the flux, we say the flux from the star is 1, right? Then you can see that there's a fall in the flux, right? And that is basically because of the planet coming in front of the face of the star. And therefore you have this fall coming over here. But if you actually look at this fall, how much is this fall? So you can see that if this is 1, you can see this is 0.06, right? So it's a 0.6% fall in the flux. So often in most of the Kepler cases, you'll see that this dip in flux is barely a 1% dip, okay? So you have a 1% dip in the flux, and that is the indicator of the planet being there. But what is considered is that you should notice this 1% flux for a minimum of 3 transits, okay? 1, 2, 3. If you can observe it for a minimum of 3 transits, then you can say that this is a potential exoplanet, right? Because you're getting a fall. I must also mention that you can get such a fall if, for example, you had, a binary star in the case of a binary star also, which are called eclipsing binaries, you can also have a fall in the brightness of the star, right? You can have this dip in the light curve, right? And therefore, a lot of people who study binary stars, they also use Kepler data, because Kepler light curves for binary stars are also there. When you get the light curve, it is your job to figure out whether it's coming because of a binary star or whether it's because of a planet. But what I'm going to show you today is that if we actually look at this light curve, which we get from stars, we can find out various parameters. So that's what we are going to do today, that we are going to use Kepler data to actually find, number one, the orbital distance of the planet. That means the distance of the planet from the star. How far is the planet from the star? The second thing is to find the radius of the planet, which we will be doing today. We will also find out the mass of the planet. How do you find out the mass of the planet? The temperature of the planet. And finally, we will also make some kind of a speculation or some kind of an understanding of the chemical composition of the planet. So what I'm going to do is I'm going to actually walk you through data analysis of Kepler data for a single exoplanet, in which we will derive all these parameters, right? And you will see how you can actually use Kepler data to derive all these parameters for a given exoplanet, right? So first of all, let's start off with how do we actually access Kepler data, okay? Later on, I will talk to you more in detail about Kepler and what happened with Kepler, and then what is the present exoplanet mission which is on. But we'll do that a little later. We'll first get on to our data analysis. So I'm going to show you this. Let me stop my share, and I'm going to take you on to my browser. So please, everybody, you go onto your browser, right? And you'll be going on to this. Yeah, so I can see there are lots of people still coming in. We are the first thing, so I just for the benefit of the others, I'm going to talk about in a minute that we are basically going to do a session on analysis of Kepler data. How do we get various parameters for an exoplanet using Kepler data? We will find out the orbital distance, the mass, the temperature, the radius of the planet, and we will also find out the chemical composition of the planet, right? So I will request you all, how do we actually get Kepler data? So I want to close this. So there is a standard website which is used to look for data, and it is called the MUST, okay? It is called, you can see it like this, the MAST, okay? If you want, you can even just add astronomy, otherwise you'll hit on various other things. And what you see is MAST is a Mikulski archive for space telescopes. So essentially what this archive does is it has data from various space missions, okay? And the space missions include Hubble, Webb data will also come here, TESS data, and a whole bunch of other missions and data, which you can see over here, which includes SWIFT, Gaia, XMM, Kepler, K2, IAU. These are various space missions. We know that there is a big advantage of sending telescopes to space, right? Because if you actually send your telescope to space, you have a benefit of a better view, right? And 1 minute. So there are a whole bunch of legacy missions which can actually be observed, and the data can be got through this. So if you click into any of them, for example, let us click into Kepler. We are interested in Kepler data. So this gives you a basic outline of what is Kepler data. So what Kepler basically did is it actually observed this very small portion of the sky, okay, which is shown over here. This is a small portion of the sky. And what it did is that it actually kept observing the same stars. There are about 200,000 stars. And so at least either it observed them in two modes, either every 30 minutes or every 1 minute. This is the cadence. By cadence, you mean the steps in which you are observing, right? Because if you want to get a light curve, you are basically seeing observations over a period of time. So you say observe it every 1 hour, every 2 hours, every 5 hours, or like Kepler did it, it observed some targets for every 30 minutes and some of them for 1 minute, right? And obviously the kind of variable stars you will observe with them depend upon the cadence you are going to put, right? Because you will only be able to catch variable stars which vary with a period of a few days or a few hours, right? Because your cadence, the step with which you are observing it, is something like that. And if you want to observe it with a different cadence, you obviously need to have observations which are separated by a larger period of time. Okay, so let us now look on to this thing. So this is Kepler, right? And to access Kepler data, this is the website, and I'm going to share this with you, in which is very simple. The same website, archive STSCI. You do preps and you say Kepler HLSP. Okay, so if you actually just from that website, I'm going to share this with you on the Zoom window, right? On the Zoom chat. So I hope you all can all access that, and in the chat window, I am putting this for you, right? So please click on this link, which is there in your chat window, right? Which is there in this thing. So I hope you all can see this, and if anybody is having a problem, please tell me. Yeah, you're most welcome to stop me at any point. If you are, we all need to be going together, right? That's the one issue with a hands-on session, that since we are all moving together, I hope you all can all see this, the website, right? I hope everybody can see it. If you have an issue, I've given the link on the chat window. Otherwise, you can go to it from the MUST archive, from MUST itself. It will give you this thing, right? From this itself, you will get it, right? Okay. So I hope you all can see this page. And what you see is, so let us look at, these are some Kepler sources. So what Kepler did is, as it started observing sources for potential exoplanets, every source gets a number. So you can see that these are the earliest Kepler detections. This is Kepler 4b, Kepler 5b, 6b, 7b, 8b. So typically what is done for a Kepler observation is that the star is called Kepler, right? If there is a detection of a variation of the light, and you can see that this variation is barely 1% or even lesser than that. And then they give a number, for example, 1, 2, 3, 4, and then A is reserved for the star, right? So Kepler 4a will actually be the star, okay? And the planets, supposing the star has many planets, you'll name them B, C, D, E, etc., right? So you can get yourself familiar with this kind of nomenclature which we have for this thing. So you all would have seen it with other exoplanet systems also, that they add A, B, C, D, etc. So A is reserved for the star, and then you start naming the exoplanet from B onwards, B, C, D, etc., right? So this is the first exoplanet, which is for the source Kepler 4. This is Kepler 5, Kepler 6, 7, and 8. And what we're going to work on today is for data with, let's take the first source, which is the data for the source 6b, okay? And what I would like you to do is, there are two data sets. One is this data set, which is called the time series data. So what is the time series? You'll see it very soon. It is giving you the timestamp, and it's giving you the brightness at various points of time, right? And this one is to couple Kepler data. What was done is that on ground-based telescopes, they actually measured radial velocity, okay? And then with the radial velocity, we are going to actually use radial velocity to find out the mass of the planet. So that's why we want to use both these data sets, because a transit method does not give us a method to find out mass, okay? So we'll come to that in step by step, but we'll start in with the first one. So please click on this, which is Kepler Exoplanet. This is the time series. So you click on it, right? And you will download it, okay? So please download it. I am downloading it over here, which is my Women in Astronomy training program. This is day 1. I've already downloaded it, and you can see this file already sitting over here. So download your time series. And the second file is click on this. This is the radial velocity file. Okay, so please click on this, and you can download it in the same area where you downloaded the previous file. So please, yeah, please make a good directory folder, call this day1, and on day1 you will download this file, which is given your radial velocity.
Excuse me,
file.
ma'am.
Yeah.
Ma'am,
Yeah. Tell.
First we have that. Yes, sir, ma'am. Ma'am, first we downloaded the file that is on the left side of the table. Then
Yeah, now
what is
download the
second
right
file
one.
you wanted?
This file, the right one,
Okay, okay.
the ground-based time series. So this is what has the radial velocity data. Okay. I hope the others are also along with me. I hope everybody is fine, comfortable. You've downloaded all these data sets, these two data sets, right? This is Kepler data and this is ground-based telescope data for radial velocities, right? I hope you all have all downloaded this data. Okay. Should I share these data files on, I can even share them on this thing. In case any of you all have had a problem in downloading the file, I will try and I'm going to do that now. Where is my TP3? Yeah. So what I'm going to do is I'm also sharing both these files on your chat window. Okay. So in case any of you all have had a problem in downloading the two files, yeah, please you can also download them from the chat window. Right? I hope everybody has the two files. We have some latecomers. The data files, you can please take it from the chat window. Okay? And so that will help you. Okay. Now what we are going to basically use to analyze this data is something called Topcat. Okay? And the training program 2, in that I actually showed you all Topcat. But if people do not have it, I would urge you to download it. Topcat is a Java-based virtual observatory tool which can actually look at catalogs. Okay, so you can see that the word Topcat itself comes from tool for operations on catalogs and tables. Right. So you can go to this, if you just Google Topcat, you'll come to the Topcat page, right? And you can come to click on downloads. If you click on downloads, you can download this jar file, topcat full.jar, and you need to have Java on your system, which I'm sure most of you all will have on your system. You can download the jar file, and then you can actually run Java -jar, or double click. If you are using a Windows machine, just double click it and you can access the Java file, the Topcat file, right? Otherwise, you may have to install it differently. I hope everybody has Topcat. Is there anybody who has a problem with Topcat? Please write that in the chat window, because I had covered this in the second training program. So I assume that many of you all may already have it, right? I hope everybody has Topcat, right? If there's anybody who doesn't have it, please write on the chat and I can give you more detailed instructions. But otherwise, I will assume that everybody has Topcat. Yeah, very good. Installed on Mac. So if you're doing it on Mac, you will get that DMG file and you can do this. Okay, Urvashi, if you want Topcat, come to this website. Yeah, this website, I will share it with you. And right, and over here, you just have to download the jar file. If you have a Windows machine, you just double click the jar file and it will work with that. If you have a Unix system, then you see this, or a Linux system, you have to give this command, which I'm writing in the chat window, which is you just say Java -jar topcat star.jar. Okay. If you have a Linux system, do this. Download the jar file and run this command. If you have a Windows system, you double click it. If you have a Mac, you'll get a DMG file, and that itself you can run it and it will start your Topcat, right? Obviously, if there are people who have problems, it could be if you do not have Java on your system. But nowadays, I think most people do have a running Java on their systems. So that should not be a problem. Okay, fine. So can I proceed? May I proceed? Is there anybody who's stuck? Yeah, I can proceed, right? If there's a problem, please stop me and I will start accordingly. So what I'm going to instead do is I think I should share my desktop only. And here's my Topcat. So I'll double click I click my Topcat, and here's Topcat, right? So I hope all of you all have seen the Topcat, this thing. This is called Topcat, right? And what you do is click on File. Click on File, right? And you click on Load Table. So please click on File and then click on Load Table. Click on File Browser. And now look at the area where you had downloaded your files, right? So I'm going to go to the area where I downloaded my files. And this is at TP3, Day1. For latecomers, some people came in late. The data files are sitting in your chat, or I don't know whether you have it in the chat because it's, if you download it, came in late. So if you click on this, this is the file. You have to choose over here file format ASCII. Okay. Click over here on ASCII and click on that and say OK. That will open the file. I hope everybody is managing to open the file. So you click on OK and that will open your file. I hope everyone has managed to open their file. If you have had a problem, please let me know. Please open your file. I can again share, should I share the files? There are people coming in late or... are there any questions from people? Is everybody fine? Did they open the file in Topcat? I hope everybody's open. I'm not able to open, just double click it. Just double click your Topcat file, the jar file on Windows, and it will open. There's somebody who's asking how to open Topcat in Windows. I said you just double click it. You can hear. I hope you all can open it, see it. Has everybody managed to do that? So if you open this file, you will see column 1 and column 2. I hope you all can all see these two columns. You can see the first column. So the first column is actually what we call the Julian date. Okay. In astronomy, we have something called Julian date, which is a way of dating things so that you can identify what is the date of observations. And the second column is the flux. So the flux has been normalized to 1, and you can see that the flux is varying like this. So I hope everybody has opened this file and can see it. Can everybody do that? Is there anybody who can't do that? Then please let me know. I hope everybody has managed to open the file and see the table in this form. Can everybody see the table like this? I hope people can see the table like this. If there's anybody who's left out, please let me know. Okay. So there are people who are asking for the files. I will try to share them again. So Chitra, I'm sharing both the files on the chat, the Zoom chat. So please download both these files. Later on, you can see the video and see from where did I get the files. But till then, you can download both the files, or whoever came in late, I've shared 2 files on the chat window. Please download both those files, right? They are plain ASCII text files, okay? So I'm actually showing you to open it in Topcat. If you want, you can also open it in Excel. If there are people who do not have Topcat, you can open it in Excel. But otherwise, please open it in Topcat. And I hope you can see, if you click on this, right, this is showing you the table. And you can see the first column is the Julian date and the second column is the flux. I hope everybody's got the tables and opened it with Topcat. If there's a doubt or question, please let me know. Ajit Kumar, you load the files by opening it. Okay, in Topcat, you go to Topcat, right? And in Topcat, there's an option for file. So this is Topcat. In Topcat, there's an option for file, and you say load table. And over here, you use the browser to find the file, right? Click on this. In the file table format, call it ASCII, and you can say OK. Okay, it'll open the ASCII file. Ajit Kumar, have you managed to open it? There's you who cannot, showing error in loading the file. It's a plain text file, so there should be no problem in actually loading the file. Yeah, okay, good. Ajit, you got it. There should not be any problem in opening the file because it's a plain text file. It's just a text file which has 2 columns, right? So there's nothing very complicated in this file. If you open it even through Notepad, you will see that your... Okay, one sec, huh? I'll just no, you'll have to okay. Fine. So Sarah, I think you managed to open it. Good. So now I will show you something. If we actually, you say, okay, now if you actually, Topcat lets you actually look at data, right? This is the data which you have made up of 2 columns. Now, if I want to look at this data, if you click on this thing over here, right? This is called the plane plotting window. Click on this, okay? Click on this plane plotting window. And when you click on it, it's asking you what does it want on x-axis, what does it want on y-axis, right? So you can actually, what has happened to this? My Topcat is now creating problems. Okay, so till then I'll just check on the others. Yeah. So latecomers, please, I would request other participants to also share the files with people because I seem to be having a problem with my Topcat now. It's gone into some mode which is crazy. Let me just close it. Okay. Yeah, so I hope everybody has managed to get this. In case you haven't, please tell me. Okay, now we're getting in. I hope everybody has managed to get that. Yeah, I'm opening my Topcat again and 1 minute. I'll just open Topcat and okay. Yeah, so I hope everybody is with me and you all have all managed to do this thing, right? I hope everyone is fine. There's some more messages. I'm just checking it. Yeah, thank you. Please, everybody just check that you can open your Topcat, okay? Because we need Topcat to do our thing. Right? So I'm just showing it once again to everybody in case you have a problem. Yeah. So I'll just repeat this step again. The 2 files which have been shared, you will click on file, say load table, right? And you can say file browser and you go to the location where you saved the files, right? Which we just downloaded and go on Day1, take this one and your table format has to be ASCII, right? And here you can actually see your file, right? So this is your ASCII file. And like you can see, you have 1 column, which is the Julian dates, and the second column, which is the flux. Now what you need to do is click on this, right? Click on this plane plotting window, right? And on the plane plotting window, you can see these are our points, Okay, so this is what we call a light curve. That means Kepler is looking at some object which is Kepler 6b, and as it looks over there, you can see that the brightness has fallen, right? With this kind of a periodicity, the brightness seems to have fallen. Maybe over here they didn't have data for whatever. You can see that there's a gap in the data. They didn't have data, but otherwise there's a repetition over here. So this is showing you a periodic transit, which is getting repeated with a certain period, right? If you want to know what is the period approximately, let us, for example, if I take this dot, yeah, you can see over here down is the position, right? The position is being showed down here as, you can see it over here. It is, yeah, it's okay. Yeah, yeah. So you can see it's 2454, 2454, 9608, right? And 0.6. So 1, 2, 3, 4, 5, 6. So you have 245496.08, right? That is this. And let me go to this previous point here. I want to basically find out the period, right? So now if I look at this point, you can see this point is 245495, right? 4957, right? And 7, 5, right? So actually, if I write it, I can write it as 2454960.8 and 2456495.7.5. You can use any 2 points which you want, which are separated by this period. And if you take the difference, I am getting, say, 3.3. That means you know that the difference between this thing is approximately 3.3 days, right? But the problem is that in this 3.3 days, since Kepler will observe a particular star only after a certain gap, right? Therefore, it may not exactly be able to catch it, right? Now, what do we do with periodic data like this? See, we have periodic data over here, and you can see that the number of points are very few, right? Number of points per this thing. How do we improve this, right? So how do we improve this? I'm going to explain something to you, which you can see over here, is this, that often in astronomy, we do something called folding, right? So what is folding? So I showed you this periodic function, right, where the light was reduced or at a separation of approximately 3.3 days, right? So it looks something like this. But I have only certain points, right? I have something periodic function like this, but I have only certain points on this. I don't have all the points. And therefore, we often in astronomy do something called folding. By folding, what do I mean? Think of this as a long strip of paper. So it's a long strip of paper, and I fold each part with the folding size being of the period, right? So my function is y, right? And I fold it in steps of p, where p is the period, so that now at each point I can get more and more points to each of these parts of the curve. Now in mathematics, how can we actually fold a function? There's a very beautiful function called the modular function, right? What does the modular function do? For example, if I have the modular function of 12 with 3, what do? I divide 12 by 3. The answer is 4, but the result is the remainder, okay? In modular function, you divide a by b, and the answer is the remainder. So therefore, if I do modular of 12 and 3, my answer is 0, because the quotient is 0, and the quotient is 4, and the remainder is 0. Similarly, if I do modular of 12 for 5, what happens? 5 2s are 10. So my quotient is 10, but my remainder is 2. So I get 2. If I take 15 and I divide it by -3, right? How much will I get? I have 5, -5. So my quotient will be -5, but my remainder will be 0, right? And therefore, if I do a modular function of a and b, I have to divide a by b, and the answer is the remainder. So what happens is, this is a very good way of actually folding functions. That means if you have a periodic function like this, and I do the modular of it, I will end up folding it, which I'm going to show it to you just now, right? And therefore, I can fold it. I will get something like this, which I will show you very soon how do we actually get this. So here's my function. I want to get the modulo out of it. So click on this part which gives you the table, right? And now what you need to do is you need to right click and you say new synthetic column. Okay, so people with me who are working with Topcat, in principle this can be done with Excel also, but I'm myself more familiar with Topcat, so I'll stick to Topcat. Yeah, so click on new synthetic column, right? And here I can call this mod. Hello, is there a problem?
Your screen is not visible.
Oh, I'm sorry. 1 second. Let me just check on the screen. I'm sorry. It's not shared. I stopped that PowerPoint and I did this. Okay. It's constantly exiting. Okay. So what I'm going to do is I hope you can see this. This is my Topcat data, right? My 2 columns. I hope everybody has that. Now what you're going to do is you're going to right click over here on the top. You're going to right click and you say new synthetic column. Yeah, good, you can see. So please click on new synthetic column and say mod. Okay. Now what is the expression? You can see that this column is column 1, which has the Julian date. So I will say mod, and I can say column 1 with, and I'm going to divide it. What will I divide it by? I have to divide it by the period. And the period we've at present assessed it to be 3.3 days, right? So I will write 3.3 and close it. So what am I doing now? I am trying to fold this light curve which I had, which gives me the dips, etc. in the thing. I am actually folding this function using modular function. What does modular function do? It divides a by b, and the answer is the remainder, not the quotient, right? So therefore I say modular of col 1 with 3.2 and I say okay, right? So let me say okay. This is modular. And now what I do is I plot. Let me plot. I can plot over here. I can plot 1, which is the flux, and 2, here instead I'm plotting modular, right? So this is my modular coming over here. Sorry, I'll take this thing here. Yeah, I've made a mistake. We have to take, we will reverse it. So I will get call 2 down and I will take mod on top. Yeah. So now what you see is I have folded it, right? You remember the first, I'll show you the first plot. In the first plot, I had this, which are series of all these ups and downs, right? But now I want to use this data to the best. Therefore, what am I doing? I'm folding it. I'm folding this data so that all the period curves come on each other, right? This comes on this comes on this comes on this comes on, everything comes on each other. So I did it by doing this modular function, which is over here, right? But you can see that I do not have a very good thing. And that's basically because I have not very well estimated my, my period, right? Because I do not have the data for all points. And therefore, what I'm going to do is I'm trying to improve my estimation of the period, right? And therefore, what I'm going to do is, all of you all will also do that. You will play around with this. So I will play around with col 1, and instead of 3.3, I can say put 3.2, or let me put 3.25, right? And I will, you can cut this and copy it with Control C so that you don't need to type it every time. If I take 3.25, you can see this is the old mod. If I take the new one, you can see I'm seeing it a little better, right? This is getting a little better. In Topcat, you can adjust your axes. How do you adjust your axis? Please click on axis, click on range. Over here in minimum, you can see all your points are lying between 1.5 and 2.5. So let us take this range to be 1.5 and 2.5. And we'll take this and, right? I need to still improve on my this thing, okay? So I will take this as still 2.2 so that it becomes broader. But you can see that my points are still badly scattered, right? And like I mentioned, this is basically because of my bad estimation of the period. So let me do, I replace the same function I'm going to write it again, right? Please cut and paste. And let me just see how can I further improve this thing, right? And I will take this and let me say, I remember I did it with 3.3. Let me do 3.2, right? 3.2, right? But you see that this is still quite scattered. Okay. Now, what am I going to do is I'm going to further try to improve this. Let me further change that period. Oh God, I want to do call. Sorry, I'll do mod. Call 1. And the period, let me make it a little better. 3.23. Let me see how that works. And I will change it over here in my plot. You can see that it remembers the old ones, lets you put the new ones, right? Oh, but this has got messed. So I need to now rescale it. I'll rescale. Oh, so now you can see my plot has become far better, right? Only I need to adjust my axes. So how do I adjust my axes? I can go into axis and I can change my range. So my range, you can see now has shifted over there. So I can say it's from say 2.5 to 3, right? It's something like this. But you can see that this is also very broad, right? I can further improve this thing. I'm going to take a shortcut because I know the approximate value. So I'm cheating. But in case you know better ways of, I mean, if you can, you'll have to play around with this a little bit. This is a stage in which you have to use your patience a little bit and a little bit of other things to actually decide what is to be done. But since I know the answer, I'm going to write it down because it should. So the better approximated period is 3.245. And you can see that if I put a better period, see this is very scattered, but if I put a better period, you can see that I'll get something like this. I'll have to again rescale it. I'll rescale it and I'll put it here. So I'll put my axis, I'll put my, you see the range has slightly shifted. So, oh God, this is still not got very nice. I'm just trying to improve it further. Let me put this thing. Why is this not doing that? God. One sec. Three point 2, 3, 4, 6. This is supposed to be a good value. You'll need to rescale it every time. Here I've got my ideal one. So what you are going to do is you will have to do this a little bit the hard way. In the sense you will have to actually look for what are the adjustments you need to make to the modular function so that you get something like this, right? This I'm actually showing you what is the good one, what it should look like. I'm going to improve on the scale a little bit by making 2.9 and this. So essentially in the modular function, you are going to improve your estimate of P or the period so that you get this thing coming better. Okay, so that you just get a single nice line compared to the earlier ones. If you remember the first one, let's go back to the first one. We had this, right, which was quite a mess, right, which was quite a mess. Then what we've done with the modular function is we have folded this. We have folded it so that we can add in all these points together. And that's how we have got this nice looking curve, right? And that is what you have to do with your data, right? You have to actually estimate, use those points to estimate a good value of the period so that you get a light curve like this. Now, each of these points have been, they have been contributed by different points in the original curve, right? See, this is the original curve, which we had over here, right? The original curve, see, has everything scattered. So at different points, you have different points coming over here and that. But by folding it, what we have got is we have got all these points together, right? And that's the advantage, because now we have a single this thing. Now, this is a technique which is standardly followed a lot in astronomy when you're dealing with periodic data. Okay, if you're dealing with periodic data, then we obviously know that your observations are at different points of time, right? And therefore, if you want a good curve, you need to fold it so that you can add it. Yes, so Shubhe, Dappa is asking, can you use EF search and F tools? Yes. So in astronomy, like I said, for typically any periodic data which changes with the periodicity, we do this thing which is called folding. We fold it so that everything comes one on the other and we get a good curve. Like I told you, each of these points have been contributed by different points of observations, but we have added them all out like this, right? And this is a standard procedure which you will follow with any kind of periodic data, with data which gets repeated, right? Because the problem is when Kepler is looking at a certain source, it's not going to look at it non-stop. It's going to scan other sources and come back to the source after a certain period, right? And therefore it does not catch the source at all points. So therefore we have to fold it. Okay, so I hope everybody has managed this folding business. Okay, Anushka is asking me, why do we particularly have to manipulate the graph into a U shape? Okay, because we want to get, this is what we call a light profile. So what I told you is we are actually looking at the transit of a planet around the star, right? So what is a transit of the planet? In the sense the planet comes in front of the star, and therefore the light from the star is, it slightly dips. But if you look at how does it dip, look at this. See, this is 1 and this is 0.99. So you literally have a 1% dip in the light of the star. So like if the star was made up of 100 bulbs, only 1 bulb will go off because of the presence of that planet, right? So you just have dimming just by 1. And that's what makes it so difficult to observe exoplanets, because you need to have a precision of 1% in your magnitude measurement, right? And therefore Kepler was sent out in space, because in space you don't have any atmospheric effect. So if you get a dip like this, it is like this. And clearly, since we've added up all these periodic things, right, they all add up together, showing you that there is clearly a dip, right, with this certain periodicity. Otherwise, randomly you could not have this kind of a U shape. So your U shape is like this, and I'll show you, I think I showed you in the beginning, Anushka, there are different slightly shapes in the sense your U can be deeper or shallower, but it will be a U. You can get maybe a hump over here or something like that. That could be, supposing if you have 2 planets which are causing the dip, you can have more features which come over here. But at present, since it's a single planet in front of a single star, it's just a U. We will only have a U. Okay. So now what have we done is, by doing this, okay, so what we are going to do is, we are now going to actually look at the first thing which we are going to find out, which is the orbital distance. I can't. Mamta needs to make, yeah. Mamta, are you there? I think she's gone. She was to go somewhere. Okay, so let us start off with our first quantity, right? What is the first quantity we are going to find out? I hope you can see my PowerPoint screen. So this is our folded light curve, right? This is our folded light curve. Now, the first thing we are going to do is we are going to find out the distance of the star from the star to the planet. How will we find that out? Very simple. We are just doing that directly using Kepler's third law. Everybody knows Kepler's third law, that the square of the period is proportional to the cube of the distance, right? And therefore, if I just use simple school, Kepler's equations, which everybody knows, GMM by R squared, we just apply that to get the time period, right? And you can actually get this formula, which is A is nothing but the orbital radius, that is the distance of the planet from the star, is gm star into p divided by 2 pi squared, right, to the power of 1/3. This is this formula which you see over here. So you have to just use this formula. I hope please everybody just write down this formula. Please write it down. I will share this PPT with you, so later on you'll have it. But as of now, please have a look at it. This is gm star into this, right? And now what are we going to do? We are going to plug in these values in this formula. Okay, so I will stop the share. The only thing which we don't know is we do not know the mass of the we don't know the mass of the star. So how are we going to find out the mass of the star? To find out the mass of the star, I hope you all can all see my browser, right? To find out the mass of the star, you're going to use this website called Extrasolar Planets Encyclopedia. Okay, Extrasolar Planets Encyclopedia. I will click on this and I will share this website on the Zoom chat, right? So on the Zoom chat, yeah. So in the Zoom chat, yeah. So the time period we put, BD is asking me, the time period that we got was 3.246. Yeah, this is like I told you, I slightly cheated. I checked the value and then hence I got it on my own. But I mean, I got it. But in principle, you should try to get it on your own. Not very difficult. You just have to play around so that you get a nice U, right? So that you get a nice U shape, you do that. So now here, let's come back to this thing. What is our purpose? We basically want to find out the mass of the star. How do we find that out? We go to Extrasolar Planets Encyclopedia and click on all catalogs. All catalogs. Okay? Please, everybody, click on all catalogs. And here what happens is, this is a catalog of extrasolar planets. And you can see there are some of them mentioned over here. We want to find out for our particular planet, what is the mass of the star. And the only problem with this website is there's a certain syntax, in the sense, how do you actually give it, right? We know our source is Kepler 6b, right? But what it actually, this website requires is you say, look for Kepler-6b in name. And the 6b has to have a gap here. So you'll say Kepler 6 space b, close inverted commas, capital in and name, right? This is a slight issue with the syntax, but you have to just follow this syntax if you want to get the name of the, if you want to get the star, the exoplanet details. And we click on filter. Click on filter, and here's our planet, right? So if we click on this, you can click on this. This is the same one. And here you see it's giving us details about the star which is the central star in Kepler 6. So I would request all of you all to note these parameters for the star, right? So for the star, what you can see is, let me note it down. We'll see that the star is at a distance, you can see, of 597 parsecs. What you need to know is the mass. The mass of the star is 1.21 into the mass of the sun, right? So the mass of the star is 1.21 times the mass of the sun. The age, we don't need to worry about it. Worry about the radius. The radius is 1.39 times the radius of the sun, right? So you only need these two parameters. I'm going to mark it and share it on your chat window. This is the, I'm going to share it over here. So where is the chat? The chat is over here. Yeah. So this is the mass of the planet. And here I'm going to share with you the radius of the planet, right? Okay, fine. Now what we are going to do is we are going to substitute. I hope you can see my browser, right? We are going to substitute all these values in our formula. What was the formula? Gm star into p squared, p squared by 2, p by 2 pi squared root, right? So let us do g. What is the value of g? G we know is 6.67. Yeah, we'll handle the powers later, right? And you can see 6.67 into the mass of the star. The mass of the star is 1.21 times the mass of the sun. The mass of the sun is what? 1.99 10 power 30. So I will do 1.99. I'm just going to do the powers later, right? So this is 10 power 30. So this is the part which I'm getting in the beginning, which is this. You can note this down. 16.06 into 10 power what? One, you have 10 power minus 11 from G, and you have 10 power plus 30 from mass of the sun. Now you're going to multiply this into, we got to multiply p squared by 2 pi, right? But what do we do for p squared by 2 pi? P squared by 2 pi, p squared is 3.246. But I need to convert it to SI units. So I'm going to do that. I will say 3.246 multiplied by 24 hours multiplied by 60 minutes multiplied by 60 seconds. So I'm converting my time period into seconds, this, and I'm dividing this by 2 pi, 2 into 6.14, right? This is this. And now what do I have to do? I have to square this. So I'm going to put this to the power. I hope you all can see all this. You can see the calculations, right? Yeah, so I'm putting this. This is the square part. Now this I've got to multiply into GM star. So my GM star was what? 16.06. And there is a, remember there's a 10 power minus 11, this thing, which is 19, right? Plus 19. So this is my thing, is this. Yeah. And I will multiply this into 10 power 19, right? This is my answer. And now what do I need to do? I need to do square root of this. So I can take this to the power of 0.5. I hope this does it. Yeah. So you're going to get this thing, right? You've got 2.8. Where is my answer? You've got 2.849 into 10 power 14. But this is obviously my answer in meters, right? Now I need to convert this to kilometers. So supposing if I do it in kilometers, it becomes 2.849 into 10 power 11 kilometers, right? Okay. Yeah. Ishan, thanks. I think you help people. Okay. So we get this thing, 2.849 into 10 power 11 meters. And now I can convert this. What can I do? I can convert this to, if I want to do it, I will convert it to what are called astronomical units, right? I hope my answer is correct. Does everybody agree with my answer? Yeah, please, everybody just, I'll stop this share and I will share this screen. Please substitute it in this formula. Everybody substituted in this formula. You're obviously allowed to check in all your values. G is 6.67, 10 power minus 11. The M star is 1.21, right? Times the mass of the sun. So 1.21 into 1.199, right? Into 10 power 30. Multiplied by P. P is 3.2346, right? Multiplied by 24, multiplied by 60, multiplied by 60. Divide that by 2 times pi, which is 2 into 3.14. Square that, right? You can see you have p by 2 pi squared. You take the 1/3. I took the square, I took the root. So that's why I got a different answer. So I'm going to stop and I'm going to go back to my share screen, which was over here. Here, we got this answer because I had taken this thing. I'm going to square this, right? And now what we actually need to take is I need to take the 1/3, 0.33. Yes. So I've got to get this. Is this the correct answer? Have people got this answer? Is everybody, what answer have people got? Should I repeat the calculations? Should I repeat the calculations? Everyone, should I repeat the calculations? I don't hear anything. So let me first do the p squared by 2 pi, right? Which is 3.246 multiplied by 24, multiplied by 60, multiplied by 60, right? I'm going to divide this by 2, okay, and again divided by 3.14, right? And this thing I'm going to square it, right? So I got this, okay? And this I've got to be multiplying into GM star. So I'll multiply this into G is 6.67 and M star is 1.21. 21 into 1.99, right? And I have to multiply that into 10 to the power of 30. Sorry, 19, because I have from G I have minus 11, from this I have this. So I will have to take this to 10 power 19. And this is my answer. And now this answer, I've got to take the cube root of this. So I will take x power 5 and I will take 0.33, right? So I will get this 54555. So this is in meters, right? So if I want to convert it to kilometers, it will just become 5455542. Yeah, 5455542.43. This will be now in kilometers, right? Okay. Now I hope you all know that the distance from the Earth to the Sun is called an astronomical unit, which is 150 million kilometers. So I'm going to measure this distance in terms of astronomical units. So I will divide this by 150 million kilometers. So I do 150 and then I add 6 more zeros. 1, 2, 3, 4, 5, 6. So this will give me the answer. I made a mistake. I've missed some. I missed another 1,000. Oh, sorry. I did not. This is still in meters. So I need to further divide it into 1,000. So I'll have to further divide this into 1,000 and get this. So this is my answer, right? So for this particular exoplanet, the distance of the exoplanet from the star is only 0.036 astronomical units, right? Now, 1 astronomical unit is the distance of the Earth from the Sun, which is 150 million kilometers, right? But here in this case, we are getting this. So this basically shows me that this planet is very, very close to its star. It's at a distance of only 0.036 astronomical units, okay? 0.036 astronomical units. It's so much closer to its planet, okay? So this is the first piece of data which we have, which is our thing about the orbital radius, or at what is the distance of the orbit of the star, right? I hope everybody's clear with this, and I'm just checking questions. Please put your question if you, yeah. So 6 point, yeah, okay. You, Urvashi, you have 6.86, this thing. And then this you'll need to divide it by 150 million, right? So divide, because we want to convert it to astronomical units. So we'll do divide by 150 into 10 power 6, right? So that is basically 6.8983 divided by 140. So you'll get either 0.04 maybe. I'll just check. Let me see, 6.839. I can, 1 minute, 6.839 divided by 150, which is 0.04, right? So some of you all may get 0.04, 0.03, something like that. That's the kind of answer you are going to be getting for this, right? Which is the distance, this is the distance of the planet from the star, which, like I told you, is something very, very small, right? We are actually seeing that this distance is very small. It is only, it's very close by, right? Now we'll proceed ahead and we are going to do this next step. All this is described in this PPT, is we want to measure the size of the planet, okay? How do we measure the size of the planet? Now, you know, what I think it was partially shown in this. No. So I will actually show you an earlier slide. Yeah, here. You can see that this is the star and this is the planet, right? So what is the difference in the flux? When you're saying 1% of drop, what are you saying? You are basically saying that the ratio of the areas, the area of the planet to the star is 1%, right? And therefore, and if you know the radius of the star, you can obviously then find out the radius of the planet. And that's exactly what we are going to do now. So what we are going to do is, if you take the total flux minus the transmitted flux, that is, this is the delta flux, right? So your delta flux is, for example, 1. 1%, right? And divide that by the total, this thing. This is nothing but the ratio of the areas, the area of the planet and the area of the star, right? And that ratio is nothing but what? This area is pi rp squared divided by pi r star squared, right? And therefore, if you look at this, if I divide this, you'll get 1 minus f trans by f dot is equal to pi rp squared divided by pi r star squared. So that means my rp, my radius of the planet, is nothing but radius of the star multiplied by root of 1 minus f trans by f dot, correct? Okay. Now f trans by f dot, I have it from my data. And therefore, what I'm going to do now is, let us look at, okay, we won't see this. I am going to share instead, okay, let me share the whole screen. And we are going to look at this is our plot, right? And here, what is the difference in our flux? You can see this is 1. And here your flux, don't take the lowermost point because that is with the standard deviation. Take something in between. So if you take an in-between point, you can look over here, read down. It's written 0.9894, right? So you can see in your own plot what is the value you are getting, 0.896 or whatever. So then you're, supposing we take 0.9893, right? So I hope you can see my browser. You can see my browser? Yeah. So now the browser you can see I'm taking 1 minus, what is the drop in the flux? 0.9893, right? And it's divided by 1 anyway. So your answer is this. And what do I need to do? I take the root of this. So the root of this, I'm taking it to 0.5, is this. And this is what I'm going to multiply into the radius of the star, right? Radius of the star we already found out. Radius of the star was, it's a little bigger than the sun. I think we got it something like 1.39, right? So it was 1.39 times the radius of the sun. Radius of the sun is 6.9 into 10 power 8. Right? So this is it. So this is the radius of our planet. Okay? This is the radius of our planet, which is 9921005. Okay? So please note this down. We have this. Now, often when we talk about planets, we obviously talk about in terms of mass of Jupiter, right? So you can Google and you can look over here, say the mass of Jupiter. Here's the mass of Jupiter. Sorry, not mass. We wanted radius, not mass, radius. Sorry. So we take the radius of Jupiter as this, 69911. So what I can do is, I will divide this value which I got, I will divide it by
Ma'am, it's in meters, right?
yeah. That's you're right. That's right. So I should. That's what I was wondering. My value will come to less. So I will divide it by this thing. Yeah, you are right. Thank you. So I am going to take it. What is the value? 69911. Okay. So I'll divide it by 69911, and I add 3 zeros, 1, 2, 3. So that's it, right? Thank you. Thanks for the prompt. But now you're seeing it is 1.4 times the radius of Jupiter, right? So this planet is slightly larger than Jupiter, right? It has the mass is, how much did we get? I remember. What did we get the mass to be? Have we done mass as yet? No, we'll do mass later. Sorry. So this is the radius. The radius is approximately 1.4 times the radius of Jupiter. Okay, very good. Now I'm going to proceed ahead and we are going to look at the next quantity. The next quantity which we are going to find out is, we are going to find out the temperature of this planet, right? This is the temperature of the planet. How do we find out? I hope you can see, right? So how do you find out the temperature of the planet? The temperature of the planet, we use the very simple Stephen Boltzmann's law, which all of you all know, that the luminosity of an emitting body is sigma times T power 4 into its area, right? And let us assume that the planet is in equilibrium. What do we mean by the planet is in equilibrium? It's not getting hot and it's not getting cold. So that means whatever falls on it, it emits it, and in that way it's in equilibrium. So we can say that the emitted light, whatever is the emitted light, is equal to the absorbed light, because my planet is in equilibrium. Emitted light is equal to absorbed light. So the emitted light is this, right, which is sigma t power 4 pi rpc squared. Now what is the light which is sent to it, which is sent by the star? The star sends how much? Again sigma, but it becomes T star, right? The star has some temperature. So sigma T star power 4 into what? Into this thing, right? Your pi r star squared. And the other problem is that the planet is only going to get the part which falls on its area, right? This is the area of the star, but the planet only gets what falls. So what you're getting is only that fraction, right, which falls in this, right? And therefore, here what happens is when we take it, we have to take it with respect to this thing. So you'll get, if now we are just getting a ratio of, you'll see all these terms cancel off, your sigma, 4 pi, etc. And here we've introduced another term over here called alpha, right? Now, planets are not perfect reflectors. So if you throw light on a planet, right, the planet does not, if it was absorbing everything, then it would be a perfect black body. And the other option it could be reflecting everything, right? But the planet just partially reflects. And generally planets have a value. So this is called the albedo, or the absorption coefficient. And this absorption coefficient for planets is approximately 0.07. Okay, that is the approximate value for alpha. And therefore, we are now going to substitute all these values in this formula, that the temperature of the planet is temperature of the star multiplied by 1 minus 0.07 into radius of the star squared divided by a squared. Remember, this radius of the star we already found, we already found out the radius of the star, right? We had, 1.39 times our sun. And we already know our this thing. This is our distance of the star, of the planet from the star, which is 0.04 astronomical units, right? We already know this. So now we are going to substitute all this and find out the value of the temperature of the planet. So I'll stop share and we'll again go back to our calculator and let's have a look. So in our calculator now, what are we going to do in the formula that we have for temperature? We are going to do temperature of the star is what? It is 5647, right? That's what we had found out, 5647. Did we find it? Did I show that to you? Or okay, we didn't. You see this? Sorry, I didn't show this to you all. But here, this is the same all this thing where you can see that the temperature of the star is 5647 Kelvin. Okay, from this point. So I will share that with you all in the chat screen, in the chat, that the temperature of the star is this. Okay, and let us now do this, which is here. 5647 is the temperature of the star. I'm going to multiply this into what? I'm going to multiply it. Now all these things have to come to the power of 1/4, right? So that's the problem. So let's do that 1/4 thing first, and then we do this 5647. So first, let us do 1 minus alpha, which is 1 minus 0.07, right? Which is this 0.93. This I will multiply into what? I am going to multiply this into radius of the star, which is 1.39 times radius of the sun. Radius of the sun is what? 6.9 into 10 power 8 into 10 power, into 10 power 8. Okay, and this is divided by, this has got to get divided by that distance, the A, right? So I am going to divide this by A, which is 6252 into 10 power 6. Some of you all have slightly different value. That's okay, don't worry about this. So 6 to power 10 power 6. And all this part also, I will have to, I'm sorry, but I will have to add a a thing over here. This is this, but I'll have to add, I need to have this thing over here. Oh God, let me, I need to square this, right? So I will square this thing. I will multiply it into the same factors. So I will take this. I'm sorry, this cat. It's not letting me go more ahead. I'm sorry, but this calculator is not okay. Oh God, 1 minute. I'll just repeat it. Let me do first the r squared by a squared part. So I'll do that. Let me remove this thing. Bah, I'm sorry. I'm just going to remove all this. I'm sorry for this thing, but let's take it as 1.39. This is radius of the star multiplied by the radius of the sun, 6.9 into 10 power 8 divided by 6252 into 10 power 6. Okay, this is my r star squared divided by a squared, which is this. This thing I am going to square it, right? And this I will multiply 0.93, right? Okay. Now this thing I will take it to the power of 4, 1/4. So it will be to the power of 0.25. One minute. Yeah, I'm sorry. It's 0.25. And this, I'm very sorry. I think I've made some mistake. Please, others, please try to calculate it. I will just repeat it, right? So I'll just stop over here and show you what I'm trying to calculate before you get lost. Here, we are substituting it in this formula, okay? Temperature of the planet is temperature of the star, which is 5647, multiplied by 1 minus alpha, which is 1 minus 0.07. Here, R star is 1.39 into 6.9 into 10 power 8, divided by 6252, 10 power 6. We square this thing, multiply by this, and take the 1 by 4th root, multiply by this, okay? So please just see if the others have managed to calculate it. No, Urvashi, what you've got is wrong. Your decimal point should have been 1 ahead. So typically you may get something close to 2000 degrees Kelvin. Huh?
Temperature of star is outside the number.
Huh, correct. Yeah, it's outside the 1 by 4. Oh, so I've taken it inside or no? Okay, so let us just once again try to do this calculation for one last time. Because it's a simple calculation, nothing much. I hope you can see this thing. So let us first do the r star squared by a squared, right? So r star is 1.39 multiplied by 6.9 multiplied by 10 power 8, right? Divided by, I don't know whether I put this thing properly. 6252 into 10 power 6. Okay, so this is my part, which is the this is what? This is r by a. This is just r by a. This is just r by a, which is this. Now I'm going to square this, right? I'll square this and get this, right? Now I will multiply this into 0.93. Yeah, which is this. Now I will take this to the power of 0.25, which is 1/4, which is this. And now I will multiply this into 5647, which is this. Very good. So this is the temperature, which is 2156. So I'll stop share. And if you remember, we got 2156. So Urvashi, yeah, correct. Nanjan, you got 2194. That's good. 2172. Very good. So in short, you have to get something close to 2000 degrees, right? Now, typically a planet like this is what is called a hot Jupiter. What is a hot Jupiter? You can see this temperature of this planet is 2000 degrees. It's hot because it's very close to the star, right? It's only 0.04 astronomical units from the star. So it's really close by. It's really very hot. You saw that that its temperature is that of this thing. Now we'll do another one, which we'll find out the mass. Yeah. So and the radius also, you know, is 1.4 times the radius of Jupiter, right? Now we'll do the last one, which is finding out the mass. Now for the mass, we have to use radial velocity data. We cannot use transit data. So therefore, what we are going to do now is we are going to use, in Topcat, you are going to click on this, click on File, and open the radial velocity data. You remember there was a second file which I had given you. So say load table, right? And now you will load that radial velocity file, the second file, okay? When we see the two files we downloaded now, the second one has the radial velocity data. So we'll take the radial velocity data and we'll take that, okay, right? And let's have a look at the radial velocity data. What you can see is that this is using the Keck high-res spectrograph. Okay, this is a spectrograph which is there on Keck telescope, in which this is the Julian dates, and this is the velocity, the radial velocity. So you can see that there's a time when the planet is coming towards you, and there's a time when the planet is going away from you, right? So the planet has positive, negative velocities. So if I try to plot this, I can see it over here. Look at this plot, and this is what this plot looks like. So you can see that the velocity, there's a point when the velocity is positive, then the velocity becomes negative, then it becomes positive, and you know, you have something like this. This is the radial velocity data, right, for this planet. Now, how do we use this to actually find out the, I hope you can see my PPT. You can see my PPT. Okay. So we are going to use this formula now to get the mass of the planet, which is the V star max, the maximum velocity you have from radial velocities, divided by sine I. Okay, we do not know what is the angle of inclination. We will assume it is 90 degrees, so we take sine I to be equal to 1, right? But in principle, that's not exactly known. Here we take this value, which is our orbital radius, 0.04 astronomical units, multiplied by the mass of the star, divided by g. See, we are just using Kepler's laws in this, right? We are using mv squared by r, right? We are using that formula, and we are using that to basically get the value of the mass. So we are going to use this formula to get the value of the mass. So let us now go to, I'm going to escape, and we will go to Chrome. I hope you can see my browser, right? And now we are going to do our final calculation for the mass of the star. So what do we have? Oh, but before that, I should help you, I should make you have a look at what is the maximum velocity. So here is our velocity. I hope you can see my Topcat plot. You can see the velocities you see over here. This is 69, right? And here you can see this is 67. This one is 77, right? So this is 77 meters per second. Okay, this is all SI units. So this is 77 meters per second, which is the maximum velocity. So this is the Vmax we are going to use in our formula, minus 77, which we got from the radial velocity curve. So we have to always remember that for exoplanets, if you want masses, you have to have radial velocity data. Okay. The other parameters you can get from transits, but for a mass, you need radial velocity data. And therefore, generally what is done, like was done in this case, that you observe the planet using Kepler data, but then you use the ground-based telescope. Once you, identified that this is a potential planet, right? You know that this is a candidate planet or whatever. Then you actually use the spectrograph to observe this planet so that you can get the radial velocity data. And that is essential for you to get the mass of the planet. And I'll soon explain to you why is mass so important. So now we are going to find out the mass using this formula. Right, this is the formula. Vmax, where we are putting 77, no need of minus sign, 77 divided by 1 into root of, this is 0.041 AU into mass of the star. Mass of the star is 1.3, and you'll take G. Yeah, you can ask your question. Yeah.
Ma'am, it's 75.9.
Yeah, that's fine. That's fine. It may slightly vary for different people. You can take that. Yeah, it will slightly. That's fine. You can take 75.9. No problem. Okay. So that's fine. So I'm going to my Chrome. Our values may slightly vary. That's okay. So what am I doing? I'm going to first, let's do the root part, which is A m star divided by G. The A value I had calculated was, you can use the value that you have, or you can take 0. Oops. Yeah, okay. 0.04 astronomical units. So that means 150, 1, 2, 3, 4, 5, 6. Yeah, astronomical units multiplied by the mass of the star. The mass of the star is what? 1.4. Mass of the star 1.21, sorry. 1.21 into mass of the sun, which is 1.99 into 10 power 30, right? So this is my A multiplied by m star, right? This is this, correct? This I'm going to divide by G. G is what? 6.67, right? And G has a power of -11. If I take it up, right, it will become +11. So I will multiply this, so into 10 power +11, correct? And now this, what do I have to do? I have to take the root of this, right? This I have to take the root. So I'm going to take this on top, and I'll take the root. Oops. I'm going to take the root 0.5. Okay. So you're getting this 4.65 into 10 power 23. Actually, my answer is not very correct. Let me just 6252 also had a 10 power 6. Okay, I'll just repeat the calculation. Just a minute. Let's do A. A is 0.04 into 150 into 1, 2, 3, 4, 5, 6 multiplied by M. M is 1.21 into 1.99 into 10 power 30, right? This is correct. This is A into m star, right? Correct. This is this. This I'm dividing by G. G is 6.67. This I'm multiplying into 10 power 11, because G has a 10 power -11. It comes, the numerator becomes 10 power +11. This, correct? Now what I have to do is I have to take the root of this, correct? So I'll take the root of this. Now I am going to multiply this. I've got to multiply this into 75.7, right? Somebody said they got 75.7 also, right? Even I think I will. Whatever, this is your Vmax. Your Vmax is 75.7 or whatever. And you get this, right? Which is 3.5 10 power 25. Actually, I've got a little lesser value. Okay. So this is the mass. Okay. Did people get the same value, or they got different values?
Approximately 3.4 into 10 to the power 25.
Correct. I've got 3.5. Okay. Now what we want is, if we want to now convert this in terms of mass of Jupiter, right? Because for all exoplanets, generally we convert it to mass of Jupiter. So instead of radius of Jupiter, I will make it mass of Jupiter, which is this 1.8 into 10 power 27, right? So I'll just note this mass which we got. We got this, and I want to divide it by 1.9. Okay. So let us do this. I will divide this by 1.9. Sorry. Actually, I should have made brackets. 1.9 into 10 power 27, which is this. Actually, there's something wrong, because I have got to get the mass not so low. Something is wrong with this mass. Did anybody get different values? Ideally speaking, we should have got 0.63. 0.63 times mass of Jupiter. Did others get other values? Please let me know in the chat. What is I? I is the inclination. Varenia, I is the inclination of the orbit. Okay, because you don't know, this is the star and the planet, you don't know what inclination is there of the orbit. So that is giving you I. So I is counting from up to down. So if we count it to be 90 degrees, we took I to be 90 degrees, sin I to be 1. We are taking it as though we are seeing it flat, edge on. But that is an approximation, right? In reality, it could be different, right? So that is the slight error we have when we are anyway doing transits. Okay, so that is what is I. Are there any other questions? Anybody else did the mass calculation? Please have a look if you had the mass calculation using this formula, right? Okay, so you'll use the mass calculation using this formula. I don't know what went wrong in my calculation. It should come about 0.63 times mass of Jupiter. Should come to be that. Okay. Now, what is the interesting thing now that we know the mass of the planet? Why is that important? Because we can use that to actually find out the density. So I'm not continuing with the mass thing. I had a slightly wrong value. Please, everybody check your calculations. I'll also check mine. And tomorrow when we meet, I'll just check and tell you. But I've already calculated it and I did get a correct value earlier. But now it's for some reason coming a little off. Right. So now we've got the density. So let's assume we have the mass, we have the density. And using this, you can actually study the composition of the planet, right? Now, because we know for the planet, we know its temperature, we know its mass, we know its radius, we know its orbital distance, right? And if you look over here, obviously, you can get the density. And typically, these are lab simulations, which were done by Gillon in 2007, where what they did is that they found out for different planets of different masses and different radii, what is the composition, right? So typically, if you have Venus and Earth, these two planets have a mass somewhere over here, a radius somewhere over here, and this is the kind of composition which you can see as pure iron, pure rock. Okay, so rocky planets, iron planets will have a smaller radius and a mass of this kind. This is in terms of units of mass of the Earth. That's why it's 1. Here the units are mass of Jupiter. So therefore you can see it is lesser, but if you're doing it in terms of mass of the Earth, it is coming over here. So these planets come in this region. While, so this is Venus and Earth. If you look at Uranus and Neptune, these guys have larger masses, but they have larger radii also. And therefore their composition is close to ice, hydrogen and helium, right? Because what you see is mass by radius is nothing but, it's giving you density, right? Mass by volume. And volume is nothing but 4 by 3 pi r cubed. So if you know the volume, you can get the density. And therefore here you can see that this is where Neptune and Uranus lie, right? Pure ice, pure rock over here in this region. But Venus and Earth were in pure rock, pure iron. Now our planet, exoplanet, we actually, which we didn't get very well, it was supposed to come somewhere over here, 0.63. Somewhere over here, 0.63 is supposed to be the value for the mass of it. And the radius, if you remember the radius, we had it in terms of RJ, we had this 1.4, right? 1.4, somewhere here. So in short, our planet should come somewhere over here. So you see that even hydrogen, helium, for example, Jupiter, Saturn, they lie over here. So this planet of ours is like one big bulky gas planet, which is made up of hydrogen and helium. Yeah, it's made up of light elements. And this is its approximate location. So what you actually saw that by doing this analysis of Kepler data, we got all the important parameters for the given exoplanet, right? Like I told you, we got orbital radius, we got mass, we got radius, we got temperature. All parameters for this exoplanet were derived just by using Kepler data as well as radial velocity data, right? And So that is what we actually did. Like we found out that this planet is essentially a hot Jupiter. It's very close to its sun, and that is why it's so very hot. The temperature is more than 2000 degree Kelvin, right? But its mass is lesser than the mass of Jupiter, but it's larger than the radius of Jupiter. So this thing is a real fluffy planet, right? Which is very low density. We didn't do that today, but you all can try it out. Since we have the mass and we have the radius, you can actually calculate the density, right? You'll take mass divided by 4 by 3 pi r cubed, and you will actually see that this planet also has a density less than water. Okay, and we know our outer planets, for example, Saturn. Saturn also has a density lesser than water. So if you had a tub which was big enough to fit Saturn, Saturn would have been floating. And similarly, Kepler 6b would also have been a floating planet. It would have been floating in water, right? So I'll end the thing with this story. And I hope it was clear to you. Doing hands-on online is a bit of a troublesome thing, so I'm not very sure whether everything got conveyed. But you all are most welcome to ask me questions if you have any doubts, right? I will be emailing this presentation to you today so that you can already start doing the assignments. This is what we did 6b today, but the assignment would be, this time I've decided to do assignments at 2 levels. So the level 1 assignment, right, would be you repeat this procedure for any of these above tags. We've already done 6b, so you do it for 4, 5, 7 or 8, right? Again, finding the data from the source I showed you. All the links and all the formulae are there in this PPT, which I will mail to you. So you repeat the procedure for any of the above targets. And the level 2 assignment, which I would like you to try to do, is to do this analysis with a Jupyter notebook. Okay. So what I'm going to do is, I can also share this with you. 1 minute. I'll share this with you. If you go to the Kepler website, right, you will actually see that the Kepler website is a very helpful website. And here there are various details. Okay, so I will show you this. If you actually go to the, where is this thing? Okay, this is just for an example. How would you actually write your Python notebook, right? So you typically, if you want to use Kepler data, I can even send this to you, but you can try doing it. Supposing this is this thing, you have to actually see how will you import data. You will download the data the way I showed you. If you want, you can actually query Kepler data using AstroPy, AstroQuery. We had a session on AstroQuery in the